Okay, so welcome everyone and to the third lecture of our GPU programming. So today we'll be learning about, so first of all, a brief recap about a previous lecture. So in the previous lecture, we saw different variations of Hello World program. We also saw how to launch kernel and how to write the kernel using something known as global keyword. And we saw how to launch kernel with multiple number of threads. Then at the end, we saw a simple application of printing all the squares of all the squares from 0 to 99 using multiple threads and without loop. So yeah, there we stopped yesterday. And for today's agenda, we have to cover so today we will be covering how to transfer the data between CPU and GPU, how the typical CPU GPU work. How CPU GPU communicate with each other, and what's the typical uh, CUDA program flow. And yeah, probably if we get time, we'll also see how is the thread organization in the GPU. So that's a brief outline for today's lecture. So with this, let's get started. Uh, yeah, so a brief recap. So this was the last slide that we saw yesterday. So there was this for loop which was printing square of the numbers from 0 to 100, and we were interested in writing the CUDA code corresponding to it. And as you can see, we were printing inside the kernel, and there was no loop involved here. Now, okay, this is fine. But let's say that we are interested in so let's say we are interested in not printing squares in the kernel, but let's say we want to do something else. Let's say we want to store this result, store this square of numbers, square from 0 to 99, square of numbers in an array, and want to get that array, want to print that array on CPU. So that's going to be our next class work. So given this code, given this C code, uh, where we are just storing square of the number in the particular index. So zeroth index in the array A, will be storing the 0 square. One array index 1 will be storing the 1 square, and so on. And we would, hello, is there any question? Okay, so we would like to write the CUDA code corresponding to this serial C code, and obviously our main goal will be to parallelize this for loop in the CUDA kernel. And I would like each and every one of you to try out how can we write the CUDA code corresponding to this C code. And I'll wait here for a few seconds for every one of you to try think about how we can uh, parallelize this code, or write the CUDA code corresponding to this serial code. Yeah, so I'll wait for a few seconds here, and request every one of you to try and post your answers in the chat. Let me get back to the chat so that I can see. I guess no one has. I'll go back to the slides then. I hope everyone is trying. I guess we have a lot of people. Okay, no problem. Yeah, I'll turn off the video for saving the bandwidth. I'll turn off the video for now. Yeah, so please try writing the, so for those of you who have joined now, please try writing the CUDA code corresponding to this uh, serial C code, and we'll discuss a couple of things about it.
Sir, I don't have a chat option.
Oh, I mean, it's there.
No, it's
It
not
is.
there for my case.
Oh, is it?
Yeah.
Are you sure? I mean, are you using app or are you
Yeah,
joining?
I'm using laptop desktop application. I don't
Okay,
have that option.
chat. Okay, if that's the case, then you can tell your, I mean, briefly tell your approach or something. But I don't understand why don't you have chat option, because chat is not disabled for anyone actually. Uh, Meanwhile, I
I
mean,
don't know.
is your, I mean, you are joining it from desktop, and I mean, are you using
Laptop.
the team application or you are
Yeah, team
using it
application.
from? In that case, it should be there at least. I mean, I'm not sure what's issue, but I mean, issue with the application or something, or issue from mind. I don't know, but it should be there.
May I join with the browser?
Yeah, please try doing that. I guess you should. I mean, even with app also, it should be there. I'm not sure what's wrong with
Okay, sir, I'm trying it.
it. Is there any?
Maybe sometimes they should change the organization above the account setting. Try changing organization. Maybe that is why it's happening.
Okay, I will try. Thank you.
Okay, yeah, sure. Please try. Yeah, meanwhile, I request others to try out this code, writing CUDA code corresponding to this code. I'll wait for a few more seconds and then we'll discuss the solution as well as see the other people's solution in the chat. Okay, so moving back to chat. Okay, I think one of them has pasted. Aslia CUDA.h. Okay. I'm unable to understand what printer. Mm. Okay, Ramasamy, are you trying to uh, use? I mean, I am unable to understand your code. What are you trying to do? Okay, you are just printing squares as we did in previous lecture.
Yeah. Sorry, that is not A of I. Just
Yeah.
printing the squares. Sorry,
Yes,
I'm
it's
trying that one.
yeah. We want to store those squares in array. So
Yeah,
that's
that's
our,
what.
yeah.
That's what.
So I request you people to. We'll soon be discussing it, but please try it out. Okay, so in browser chat is coming for me and not for software. Okay, just in case it's happening with someone else, then you can try joining it from browser also. Uh, it might solve the issue. Hello, am I audible? Hello.
Yeah.
Yeah, so let's go back to the slides. So, okay, so uh, this is the CUDA code corresponding to that the serial C code. So, couple of things that we should observe in this code. Okay, first of all, first thing that you should note is that array declaration is same here. I mean, we are declaring the array on CPU. Uh, then we are declaring this pointer d star a, which is a pointer on CPU, and it will be pointing to some memory location on GPU, and that's why it's called d star a, and d stands for device. And then we are declaring this variable I, and then this is important. We are allocating memory on GPU using CUDA Now you might ask why we need to allocate the memory on GPU. Why just can't we use this array A, which is already declared on CPU, and pass in the kernel, pass to the kernel? But yeah, as probably I mentioned in some of the previous class, that GPU and CPU have different memories. So whatever you declared on the CPU might not be accessible on the GPU, and hence we need to declare separate memory on the GPU, and that can be done using cudamemcopies. So here in this case, we need to allocate separate memory for the array A on the GPU. So that is done using cudamemcopies. And okay, so cudamemcopies takes two arguments. First is the address to the pointer DA, and second argument is the number of okay, second argument is the size of the memory that we want, like uh, n, we want the, I mean, array of size n into size of int, which is the size, I mean, n integers. So that's one thing. And after allocation, after this CUDA we will have memory of size n integers allocated on GPU. Now what we will do is now, okay, and yeah, one more thing is this DA will now point to this newly allocated memory on GPU. So let's say if that memory has allocated, I mean, memory has been allocated from 1000 memory location, then DA will have that address 1000. DA is a pointer on CPU, but it is pointing to some location on GPU. Please make note of that. And now we are calling the kernel using n threads, I mean 100 threads actually, and we are passing this address. We are passing this pointer, which is address, which is pointing to some GPU memory location to the kernel. And now kernel has this a, I mean this address. Now please note that this int star a here declared here is a pointer declared on GPU since it's in a kernel, and it also has a address which is passed, I mean address held by DA, which shows a I mean which points to a GPU memory location. So A will now point to a GPU memory location, and we can index this using thread ID. Now we can index this array A, which is on GPU, using thread ID. And as we did it in our previous example, we can use thread ID, unique thread ID, using thread ID x.x, which will give us that unique thread ID, and can multiply it to get the squares and store in that particular memory location. It will have same effect as a of I equals to I into I. So here I is the thread ID. I mean, we will get unique I using the thread ID. And once this kernel is over, I mean execution of this kernel is over, I mean after that we have this cudamemcopy. It's important to note what it is, what is it. So cudamemcopy is what cudamemcopy does is it transfers the data from CPU to GPU as well as GPU to CPU. Here we are transferring it from device to host, which is here, meaning we are transferring it from GPU to CPU. And so its typical syntax is: first is the destination address, second is the source address, third is the size of the memory, I mean size of the data that we want to transfer, and fourth is in which direction we want to transfer, from host to device or from device to host. That is the fourth argument. So we have 4 arguments in this cudamemcopy, and since we are transferring it from device to host, which is from GPU to CPU, first argument is the CPU array, then the GPU array, And then there is n into size of it, which says that we want to transfer n integer values from GPU array to CPU array, which is D8. Yeah, so that's about CUDA memcopy. And yeah, once that transfer is completed, we are done with it. We can simply print these values which are in array A on the CPU. Here, please note that this is being done on CPU, and then we can return 0 and just finish the main. So this code, which is corresponding to the serial code, this CUDA code, will print all the squares from 0 to 99, 0 square to 99 square it will print. So I'll probably wait here for a couple of seconds. If you people have any doubt, I'll take them. I hope you people are able to hear me, right?
Yeah. Actually,
Yeah.
could you explain the thread IDX again once more? I thought it was just like an ID
Yeah, sure.
for the thread, but here we are like multiplying
Yes.
it.
Yeah. Okay. So it's okay. Let me explain it in simple words. Thread IDX.x will give ID of thread only. So let's say if thread one is executing that kernel, then when it will see thread ID replaced by
Sir,
1. If thread
your
0 is
voice is
executing,
Hello.
breaking.
it will
We're
replace it by
unable
0.
to hear
Sir, your
you.
voice broke.
Oh, is it clear now? Probably that's because of some internet issue. Hello.
Yeah, okay, I think it's better now. Could you please repeat that last thing that you said?
Yeah, so I am saying that thread ID is the ID of that particular thread only. So whenever you write, whenever a particular thread is executing that kernel, and whenever it sees thread ID x.x, it will replace it by its ID. And we are multiplying it because we want squares to be stored in that array location, right? That's why we are multiplying. And you are correct that it will give ID only. And yeah, CUDA. What's the other questions? Which is source and which one is destination in case of CUDA memcopy? Okay, so first argument is the destination. Second argument is the source. I'll go back to the slides. So this one is the source. A is the source, and DA is the destination. Sorry. First one is the destination. So A is the destination, and DA is the source. So this CUDA memcopy tells that we are transferring data from uh, DA, which is GPU array, to the CPU array A. I hope that is clear. Sorry for that confusion initially. Okay, so sir, I am not getting thread ID. I explained. I guess it's clear now, Aditya. Is
Sir,
CUDA
one
device
question, like when
synchronized
we are
not? Yeah, go ahead.
when we are multiplying the thread ID, is it being dereferenced from the ID to the actual value, or?
Actually, it's not getting dereferenced. It's sort of like uh, there is nothing like dereference happening. It's like just you are just referring to that ID. Let's say whenever a thread is referring to that thread ID x.x, it's just getting. It's replacing it with its own ID. You can look at it in that way. There is nothing like dereferencing, I guess, happening as far as I know. I hope that's clear. Hello.
Okay, sir.
Okay, so moving on to the other doubts. Yeah, CUDA device synchronize not required. That's a good question. We'll see about it, that whether it's required or not. Sir, why are we exclusively using X in thread ID x.x? That's also a good question, Harish. Probably we'll see in this class or the next class what is the significance of X there. Sir, please explain CUDA memcopy again. So CUDA memcopy is like a data transfer operation. As I told, CPU and GPU have different memory. We need CUDA memcopy or some function like CUDA, memory copy function, so that we can transfer data across CPU and GPU. Thanks, I got it. Okay. One more thing, whether CUDA device, yeah, I'll talk about it. Whether we'll need it or not. Yeah, so this is very good question. Does copy also freeze the CUDA memory we allocated? So by default, no. There is something called as CUDA free that we should also do. I have not done in this. I mean, I have not done in this program, but yeah, there is something called as CUDA free, which is used for freeing that memory. By default, it will not free the memory that is allocated. Good question. Okay, I guess I have addressed all the queries. So switching back to the slides now, just a moment.
Sir, if I may ask, is there any difference between CUDA malloc and regular malloc?
Yes, I mean it's in its name itself, right? CUDA malloc allocates the memory on the GPU's DRAM, while malloc allocates the memory on CPU's DRAM. So
But when we
that's the
declared
key difference.
the pointer, we declared the pointer in the CPU's RAM, right?
Yeah, but that is simply a pointer. Okay, I'll switch back to the slides. Yeah, probably I
So
can explain. So this is just a pointer which is on CPU. But when we allocate memory using CUDA malloc and we pass this pointer as argument, this pointer will hold the address of the memory which is allocated on GPU. So think of it as some memory chunk being allocated on GPU, and DA is pointer rather, I mean, whether, although it's on CPU, it is now pointing to some memory location which is on GPU. I hope that answers your query. Or probably I can explain
yes, sir.
further.
And after that, actually, now we have like a pointer that is pointing into the GPU memory from the CPU, right?
Yes. That is
After that, we
DA.
are yeah. After that, we are passing that again to our function, which is going to be running on the GPU, and there we are changing it into another pointer to int
No, we
star
are.
a.
It's not changing to another pointer. So let's understand. When you pass DA, it's passed by value. Please note that this DA is passed by value. Now, what is value inside DA? What is value inside DA? DA is an pointer, so its value is the address, right? So pass by value is we are passing address here. So address of GPU's memory location, which was allocated here by CUDA malloc, is now being passed in this function fun, and now that address is held by some another pointer int a, which is now on GPU. This pointer is on GPU, and it again points to the same memory location which was allocated by this CUDA malloc and which was allocated on GPU. Please note that. So this pointer star a now has the address of memory location which was allocated on GPU by malloc, and now it can access here because in global function, which is GPU function kernel, we can obviously access the memory allocated on GPU DRAM, right? I hope that's clear.
Yeah, now I understand that part. But then from that understanding, both DA and A are pointers pointing to the GPU memory, right? So then again, we are doing like a memcopy.
Okay, yeah, okay, I got it. So you're telling that this A and this DA both are pointing to GPU memory.
Yeah.
Yeah, but please note that this A is the scope of this A is limited to this global function, and the A that we are referencing here is this CPU array. So it's not happening between two GPU memory, it's between CPU and GPU. Please make note of it. So
Oh yeah,
I
of
am
course.
assuming that
Sorry.
you know what is scope and all those things. So when we are
Yeah, I
seeing A
understand.
here, it's a CPU array. And when we are seeing A here, it's this GPU pointer. I hope you got it.
I got it.
If any one of you have any question, please feel free to ask because this is a very important slide, and I mean this is going to be very common across our next I mean almost entire our course. This malloc and memcopy will be very frequently being used in our slides throughout the
Hello,
course.
sir. Hello.
Yeah, please go ahead.
Sir, can we allocate memory on GPU's memory, like GPU's VRAM?
Yes, I mean, okay, I guess you missed it, but this CUDA malloc is the function for doing that. I mean, that thing that you told. CUDA malloc will allocate a memory on GPU's DRAM. So when we say
So,
CUDA
hello.
malloc, yeah,
Hello, sir.
please.
But aren't we like using the CPU memories pointer here. How can we allocate GPU memories memory to CPU memories point?
Okay, I guess probably you are missing something here, but please note that this DA is just a pointer on CPU. It's not a array or something. It's just a pointer. So pointer is just like it's referencing some memory location. So what this CUDA does is it allocates the it allocates the array of size n integers, and it gives it its address. Think of it like it is giving back its address into this pointer DA, which is on CPU. So CPU pointer will store address to the GPU memory location. So please note that this allocation is done on GPU. Only we have its address on CPU inside this variable DA. So it's not like uh, or how can I say, like it's not that it's allocated on CPU. It's allocated on GPU. It's just that I have reference to it on CPU. I hope that it answers your question. It's not on CPU, it's on GPU, but
Yes,
reference.
sir. I got the clarity. Thank you.
Yeah, so you can like think in this way also. Reference is like address. You might be sitting in your home, but you can have the address of someone else's home. In that way, you can think of. So that's completely fine. CPU and GPU are two different homes, and one can have the address of another. Someone who is living in a different home. That way. Okay.
Bro, one last question actually.
Yeah, please go ahead.
I'm going to guess that because we are making like a pointer on CPU side first, and then doing it on the GPU side, that we can't
Yes.
actually directly return. There's something convenient like a return statement for the GPU kernel, right?
Yeah. So this is a very good question. See, there is no way in which we can return anything from GPU kernel. So probably in previous lecture also someone asked like, is there any way to return something from kernel? But yeah, as far as I have checked, there is no convenient way in which we can return something from kernel here using int or something or int star or something. So we will need this CUDA memcopy to copy back the things and also for the allocation. I hope that answers the question. So yeah, till now we don't have that facility for returning. Okay, I guess no one have any further question, right? Or if you have, you can ask and I'll pick that up. No, I think CUDA needed for free memory. Yeah, that's correct. We need CUDA free. Sir, is there any tangible efficiency difference between C program and CUDA version of the program? Okay, for this code, I don't think that you will see any performance improvement. Okay, so your question was efficiency difference. Yeah. Okay, so for this code, I don't think, sorry. Okay, for this code, I don't think that you will see any major improvement in performance. But we'll see we'll see different codes where you will actually observe the performance difference, because here the size is very small, right? For 100, I don't think that we'll be able to see any major difference in performance. It might also happen that GPU code might perform worse than CPU code. Okay, I hope that answers the question. If there is any other question, I'll take. Okay, I guess I have answered probably most of the questions. Okay, so switching back to the slides. Okay, I think this code is clear now. But there are three things that we should observe before we switch to next slide. The first thing is that, as many of you pointed out, that there is no CUDA device synchronize in this code. So this is an important observation. And why we don't have CUDA device synchronize here? The reason is simple. This CUDA memcopy it's a blocking statement. So as we saw in our previous lecture, when CPU launches this kernel fun, it will move on, keep executing the next statements after it. But whenever it says cudamemcopy, it's a blocking statement. So what it will do is it will wait here until all the previous kernels are finished. And hence, in some sense, we don't need cudamemcopy because CPU will implicitly wait for this cudamemcopy. I mean, it will implicitly wait for all the previous kernels or threads of all the previous kernels to finish before starting the execution of this cudamemcopy. So in that way, we don't need cudamemcopy as long as we are as long as we are writing sorry, we don't need CUDA device synchronize as long as we are writing cudamemcopy. But as a good programming practice, you should write cudamemcopy after every kernel call. But here we can avoid. That's one thing. Second thing is this cudamemcopy itself. One thing that you should know about this cudamemcopy is there is something called as PCI Express bus across which the mem copies occur between CPU and GPU DRAM. So this mem copy is time consuming since there is a limited bandwidth that this PCI Express bus has. And if you're doing a lot of mem copies, CUDA mem copies across CPU and GPU and GPU and CPU, then it can become a very crucial bottleneck. So you should you should take care that you allocate sufficient number. You do sufficient amount of computation inside your kernel.
Sorry, your voice
that I
broke
wanted
again.
to make from this slide. And third, sorry, okay, is it clear now? Hello.
Yeah, now it's better.
Okay, so I'll repeat the second point that I wanted to make. So I was saying that this CUDA mem copy can be a bottleneck because the data transfer across CPU and GPU occurs through something called as PCI Express bus, and that bus has a limited bandwidth. And if you have a lot of data to transfer, then transfer through this CUDA mem copy, then it can become a bottleneck. And so the point that I wanted to make is you should have enough or sufficient computation to do inside your kernel. And after that, you should do the mem copy of the required data back to CPU or from CPU to GPU. So that was the second point that I wanted to make. I hope that was clear. And the third point that I wanted to make was from this slide is that we will need we will need to allocate separate memory on GPU using this CUDA malloc because the CPU DRAM and GPU DRAM are different. So these are three crucial points from this slide. Okay. If anyone have any questions further, I'll just quickly see. Otherwise, we'll move on to next slide. Okay. Sir, is there any need for defining prototype if function declared after main? Okay, are you talking about kernel declaration after main or something? I missed Deb. Are you talking about any kernel declaration after main? Okay, I am not sure about if we need to. Probably we need to provide its declaration first, and then we can define it after the main, as we do for C programs. But I haven't seen any CUDA program doing so. But yeah, I need to check this one. Like as we do for C program, we can declare the function first, and we can provide its definition, and then we can add its body later after the main. So I think that must be doable, but I haven't seen any CUDA program up till now doing that. So I need to check that part. Yeah, so that's it. And because of CUDA mem copy plugin, synchronize is not needed. Got it. Thanks. Okay. Yeah, because of that. Yeah, we don't need CUDA device synchronize. Okay, so I guess we should move further. So moving on to the next slide. So we have this slide, which is, I think, very simple C code. I want you people to quickly tell what will be the output of this code. I think it won't take more than a couple of seconds for you people to figure out. But what will be the output of this code? Can all of you quickly type in the chat?
Hello world.
Sure. Hello world. I guess most of you might have got it correctly. Yeah, I guess no one has typed, but yeah, the output of this will be hello world. Okay, so moving on. Now, let's say instead of printing hello world from CPU, I make this small change. I just write this D kernel and launch it with 32 threads. And inside this kernel, I print this message. Instead of on CPU, I print this message on GPU. And then I add CUDA device synchronize. Now, what will be the output of this program? I want each and every one of you to try out what will be the output of this program. Request each and every one of you to try and let me know in the chat what will be the output of this program. Then we'll discuss. Couple of minutes, I'll keep it like this so you people can see and try. Okay, switching back to the chat. Hello world 32 times. Hello world 32 times. Hello world 32 times. Error. Hello world 32 times. Error. Okay, good. I mean, at least you people are trying, and that's very good because we should try at least. I mean, even if we are wrong, we should try. Okay, switching back to the slides. So this program will give error. The reason is simple. As I explained in the previous slide, that GPU memory and CPU memory are different. And whenever you declare any variable or pointer in CPU, I mean here, whatever we are declaring as a global variable, this global pointer here in this case, char star MSG, it is a pointer on the CPU, or it's a string which is pointer to this string or character array which is pointing to the CPU. And this character array is in fact also declared as well as allocated on CPU. Please note that. So if you try printing this on GPU, it won't work. Here we are lucky that compiler itself is giving us the error message that MSG is undefined in the device code. Why? Because MSG is something which is declared on CPU, and it doesn't know what, and this is the GPU kernel. This is not something related to CPU. So it doesn't know what is MSG. And hence there is compilation error saying that identifier MSG is undefined in device code. And the key point to note here is that CPU and GPU memories are separate, and hence this is giving this error. And one more small note that I wanted to make here is that this is true for discrete GPUs. I mean, when I say discrete GPUs, it's like CPU, DRAM, and CPU is a separate device, which is it's not integrated. Or in other words, CPU DRAM and GPU DRAM are different. But there is also something called as integrated GPUs, which are somewhat integrated with the CPU itself. So they have common DRAM, and in that case, this program might work. But most of the high-end GPUs like NVIDIA GPUs are discrete GPUs, which are not integrated with the CPUs, and for them, this program will definitely give the error message, or error message, also cause program to crash. So this was the point that I wanted to make from this slide.
Hello, sir.
Any questions? Yeah, please go ahead. Yeah.
So would this program run if we declare the message in the kernel instead of making it global?
Yes, if you, yeah, just taking your question with help of this slide. If you declare it inside this kernel, inside this kernel body, and if you print it, it should 100% work. Because whatever you declare inside the kernel, probably you might remember in our previous lecture that I told that there is something called a stack. So if you declare something, some variable here inside the kernel, it is allocated on either GPU stack or inside its DRAM. So it should definitely work and it should print the correct hello world message here. But if you declare it somewhere in the main or here, then it is declared on the CPU stack or CPU heap. And in that case, GPU doesn't know, I mean, GPU don't know, like it doesn't share the DRAM with the CPU. So it will either give this error, compilation error, or will cause seg fault. Or will also can print garbage value and all those things. So we should take, I mean, we should know all these things that this uncertain behaviors can happen if we access this CPU memory from the GPU.
Sir, and also another
Yeah.
small doubt.
Sure, go ahead.
Don't we need to use a format specifier while printing it?
Yeah, that's correct. We need a format specifier, but yeah, in this case, I have missed it. But yeah, that's sort of a syntactic error. But I guess the main point that I wanted to make out of this slide was this thing, CPU and GPU memories are separate. But yeah, you are correct. We need to specify format specifier, which I have missed here. Sorry about that. Yes. Okay, it's Nilmo is saying a host variable message cannot be declared in device function. Yeah, that's correct. Uh, but it's saying that it's a warning, I guess, not error. Okay, it's also an error. Okay, cool. Is it audible for everyone? Probably there is some internet issue, but can anyone please quickly confirm if I'm audible?
Yeah, audible.
So you're audible, but it's breaking in between. Maybe it's because of your internet signal.
Yeah, there is some, I mean, there is power cut in my area, so sorry about that, but so I'm currently connected with this hotspot, and probably I guess by now it should be okay. I guess LAN is now connected. Yeah. Okay, I guess probably you won't, I mean, you won't see that issue again because now LAN is connected, so it will be much better now. Uh, Sir, is there a reason for using a pointer instead of a variable for the string hello world? No, I mean, there is no, I mean, we can also declare a character array instead of a pointer pointing to that character array. And yeah, that should also work. There is no reason behind it, any such, I mean, no specific reason for that. I guess that clears your doubt, Harish. Okay, then I'll move on with the next slide. Okay, so there is one small modification now with this program. Uh, let's say instead of declaring it as a constant char star message, I just replace it with hash defined message hello world and then print it inside the GPU here, inside the GPU kernel. Now I want you people to try out what will be the output of this program. Please try out and paste your answers in the chat, and I'll be looking them so we can understand it better. Okay, so I'll be going back to the chat. Hello world 32 times. Hello world 32 times. Hello world 32 times. Yes, I guess most of you have got it correctly. I request others also to try so that, I mean, at least trying is important, as I say. Okay, I'll switch back to the slides and let's understand why it is printing. I mean, you are correct, it will print hello world 32 times. But let us understand why it is printing hello world 32 times. So the reason behind it is that when we declare, I mean, when we define use something using hash define, then this syntax, the identifier, and then the string, something that we want to replace it. It's a preprocessor directive. So what happens is before this program is compiled, all the preprocessor directives will be processed. So what will happen is wherever this string message is there inside this code, it will be replaced by hello world. And due to this, I mean, before compilation itself, your code will be something like this: printf hello world here. This message won't, MSG won't be there, and hence it is as good as writing printf hello world. And if that's the case, this kernel launch will, I mean, it will launch and will print hello world 32 times without any issues, right? Because we are not accessing something which is on CPU here. We are just printing the string hello world, which probably you might have seen in previous lecture, somewhere in the example we saw that program, right? Printf hello world printed 32 times. So it's exactly same as that program. And yeah, it should print hello world 32 time if we compile using nvcc and run ./a.out. So key point here is hash define is okay because it's a preprocessor directive, but declaring array or a string in CPU and then accessing on GPU is not okay, since CPU and GPU have a discrete memory or DRAM, and please make a note of it. And it's okay. So moving on the next slide. So again, reiterating. So this is kind of a structure of, I mean, structure or somewhat brief overview of how CPU and GPU communicate. So they both have separate DRAM. There is something called as PCI Express bus, which I also mentioned in previous to previous slide. And in order to, I mean, in order to access something on CPU or some variable or array we have declared it on CPU, we need to make it separate copy on GPU, and then we need to transfer the CPU array, I mean values in the CPU array to GPU array, and we need to do it for each and every CPU, I mean CPU array or CPU something variable or something that we have. So CPU and GPU have discrete physical memories or DRAM, and CPU variable cannot be accessed directly in GPU kernel, and vice versa is also true. Something which is declared in GPU DRAM also can't be accessed in CPU. So this is a very important point you should always remember. Otherwise, you will see several issues with your code. And when we say that we need separate copies of this variable, now it comes to programmer to maintain the, I mean, maintain these two variables. I mean, it's our responsibility to declare a separate CPU variable as well as a separate GPU variable or copy of separate GPU variable. And it's also our responsibility to keep both of this variable in sync. So let's say if array is declared on CPU and it's initialized with some values, then it's our responsibility that we should allocate, let's say our wish is to uh, manipulate that array in GPU, then it's our responsibility to declare it on GPU, meaning allocate it on GPU, and then also copy that values of that array which are there, I mean values in that CPU array to the GPU array before we start operating it on that array on the using the GPU or in the kernel. So okay, so that was the point that I wanted to make. Any questions up till now? I'll quickly, I mean, wait for a few seconds or quickly go back to the chat.
Hello, sir.
Yes, sir.
Yeah, go ahead.
Sir, sorry, this is my tool issue. It's not related to that one. The
Okay.
thing is like I have downloaded 11.6 CUDA. I
Oh,
have installed the Visual Studio also,
okay.
but once again it is telling that NVCC fatal error, the path is not defined. But I made sure that I have given the path, added the path on the environmental variable. I don't know how to figure it out. Every time, no, I have a GPU, but I couldn't be able to work. I don't know what is the mistake I'm doing. Maybe after this class, I will send a mail to you. If you can come on Zoom or Google Meet and something, if you can help me, it could be a better thing, sir. Just
Okay.
a request if you have a time.
Yeah, we'll see. I mean, after the lecture, we'll see. Probably in lecture, we
Okay,
won't
thank
be
you.
able to because we are running out of
Okay,
time.
thank you, thank you.
But yeah, we'll definitely see after the lecture. Or probably in the mail, we will look into it. Someone else also was asking if any one of you have any question, then please feel free to
Hello,
ask
sir.
related to the content. Yeah.
So is there a possibility that we run both the GPU and CPU on a virtual memory?
Yeah, that's a very, very good question. So, okay, so one thing that you should notice, probably will come to it in next slide, that CPU can access file system directly. So concept of virtual memory is only applicable on CPU. So like virtual memory concept is something like this. So whenever you don't have enough memory to, I mean, enough DRAM, I mean, enough space in your DRAM, you can swap in, swap out uh, uh, pages from DRAM to secondary memory and secondary memory to DRAM. But okay, so GPU for GPU case, it doesn't have direct access to the file system. So virtual memory, accessing virtual memory for GPU is not possible. I hope that answers your question.
So and also another doubt.
Yeah, please go ahead.
Uh, Assume that my PC has a unified web memory with my CPU and GPU, and I try to use cudamemcopy or cudamemlock or something. What would be the case? I mean, what would be the result? Would it show up an error or anything like that?
Okay, if you have a unified memory, then in that case, I don't think, I mean, if you have a unified memory, then that memory will be common between CPU and GPU, right? So I don't think that you will get any error. In fact, you will get an benefit, like you won't be, I mean, you won't need to maintain separate copies. It will implicitly taken care by the compiler.
Yes, sir. But what if even though we have unified memory
Hmm.
and used cudamemlock or cudamemcopy,
That's
would
perfectly
it
fine.
show any abnormal actions or something like that?
See, as long as you have space in your GPU DRAM, I mean, separate DRAM or some space in your GPU DRAM, cudamemlock will allocate the memory, and as long as it is able to allocate the memory on your GPU DRAM, it will not give any abnormal behavior. But let's say if there is a case that it doesn't have enough memory to allocate, then it might give some abnormal behavior. So I mean, so talking in a very simple way, having a unified memory will not affect the functionality of CUDA is what I'm trying to say.
Sir, in like the earlier code that we did, we like made a pointer to the GPU memory, and then we told the GPU where that address is, right? So would it also work if we have like a CPU address and then we pass that address to the GPU and tell it to work from there, or will that be like segfaulted?
Sorry, can you repeat your question? I missed it. Sorry.
Earlier we saw that we made like a pointer to the GPU memory, and then we passed the address to the kernel, and then we had it work from there, right?
Yes, yes, yeah.
Yeah. So like that, can we have like a CPU address and then pass the CPU address to the kernel and tell it to access the CPU memory, or would that like cause like a segfault?
No, that will cause segfault, right? Because see, you are allocating something on CPU. Now, even though it's passing, I mean, you are passing its address, but that address is on CPU, right? So if you are, and GPU, I mean, kernel is something which is executed on GPU. Now, if you are executing, I mean, you are running something on GPU and you are trying to access something which is on CPU, then it can cause abnormal behavior. It can print garbage value, or it can even cause sec fault or something. I mean, it will cause abnormal behavior. So it's not okay. You always need to allocate it on GPU. I mean, allocate memory on GPU and then pass the pointer to it in the kernel. And that's the correct way to do. Yeah. So yeah, just like the previous thing that you told might lead to some problem. Yeah. I hope that's clear.
Yes.
Okay. Okay. Then moving on further in the slides. I hope that it was clear to everyone that CPU and GPU have discrete memories, and we need to always take care during the allocation that we maintain the separate copies and keep them in sync. So moving on, and yeah, so now we'll look the typical uh, CUDA program flow, how we will uh, work with typical CUDA programs. So first thing that we'll do is we'll typically load the data, since we want to process the data in parallel on GPU. What we'll do first is we'll load data from the file system into the CPU memory. Now when I say CPU memory, it's the DRAM of CPU, which is the RAM or main memory. Then what we will do is okay, so let's say we have copied some array or something, like let's say some matrix into the CPU's RAM. Sorry. Now let's say we want to perform some parallel operation on that array or matrix. Then what we will do is we'll transfer, I mean, we'll first of all allocate that array or matrix on the GPU using cudamemcopies, and we'll copy that data from CPU memory to the GPU memory, which is shown in the step 2 here. So that's the step 2. Once we have allocated the memory of our matrix or array on GPU and transferred that matrix data from CPU to GPU, we will execute that GPU kernel, and threads will work parallelly on that array or matrix to perform that specific task. And once that task is finished or over, what we will do is we'll transfer or copy the results back from GPU to CPU. So okay, so once, let's say we have computed that or done that matrix operation that we wanted to do using GPU kernel in parallel using multiple threads, we copy that matrix back from GPU to CPU. And once this is over, what we do is we use the results on CPU. Now, what is using this result? It might be either we want to print that result, or it might be that we want to store them back into the file system, or it also might be the case that we want to modify, I mean, we want to take the results, modify it, and again load back to the GPU memory, and again do some computation on the GPU kernel, and then again copy the result back from GPU to CPU. So this step 2, 3, 4, 5 can be iterative. For example, it can continue till we reach some fixed point, until and unless we have converged, and this can go on. And once we are done with the entire computation, we can do either printing or something that we would like with the final result. And yes, this is the typical CUDA program flow. And for each of this step, now we are going to see the operations that we will, I mean, operations or functions that we will use to do each of this step. So for loading the data, typically we need read for reading the data from disk to the CPU memory. Then for copying the data from CPU to GPU memory, as we saw, we'll need this function cudamemcopy. And the important point to note here is that we will need cudamemcopy with this parameter. Fourth parameter should be this, from cudamemcopy host to device, because the host is the CPU and device is the GPU. So host to device says that I want to copy data from CPU to GPU using cudamemcopy. And yeah, so and for the third step, calling to the GPU kernel, we have already seen that we need to launch a kernel with kernel name here. Then this 2 parameters which specifies the number of threads, and and the arguments to the kernel. So this is for calling the kernel part. Then the fourth step, copying the data or result back from GPU to CPU memory, again can be done using CUDA memcopy. And again, the point to note here is that we'll need CUDA memcopy device to host as the fourth parameter, because we are copying it from GPU to CPU, which is device. GPU is called as device and CPU is called as host. And yeah, these were the specific functions that we need for each and every step that we saw in our previous slide here. And once this is done, for printing the results or using the results on CPU, we can use our normal C functions like printf or anything for printing, or fwrite for writing it to the file system, and so on, like those functions. Any questions up till now? I'll quickly go back to the chat to see if you people have any questions. Normally in image processing, while doing FFT, DWT, DNN, we need good amount of memory, but GPU doesn't have good capacity as compared to CPU. How to tackle this issue? Okay, in that case, we probably need to load a part of image, like probably will load a tile of image. Some tiling might be done, and that tile might be processed, and that result will be copied back, and then again the next tile will be loaded, and then that tile will be processed and brought back, and that in that way we can do tile by tile. One second approach that we can use, I mean that we can use to tackle this issue, is that we can use multiple GPUs. Since memory of one GPU is very limited, we can use, let's say, 8 GPUs, and we can distribute the computation as well as the what I can say, the data across all 8 GPUs, and once all those 8 GPUs compute the results, we can bring those data back into the CPU and can merge the results. So that is one, that are two possibilities that we can use. Is there any DMA possible between host and device? As far as I know, there is no direct memory access or something like that, DMA between host and device. Everything is through PCI Express bus as far as I know. Yeah, so that's about DMA. And for the same process or operation, GPU and CPU size will be same or different? Yeah, for same process, I guess it will be different, because I mean, in CPU process, we have a single process, right? I mean, we have very limited number of threads, if we have any, in the CPU process. But for the GPU process, we generally don't launch a GPU process with a single thread. We have tens of thousands of threads on GPU. So I guess it will be different. But if you are talking about exactly same process, then it might be the case that it might be same. But I guess I'm not sure about it completely, but there might be some difference, at least in the size, because it depends, right? I mean, it depends upon hardware, how much size of stack you are allocating, how much size of heap you are allocating, and it depends from device to device. Like GPU might have different policies for allocation of stack and heap, and I mean the size of allocation of stack and heap. So I guess it might differ, but I mean exactly how processes size are determined on CPU and GPU, I'm not sure about it. Why we do not print the results on GPU kernel? Okay, why do we not print the results? So like so GPU is something like, think of it like a what I can say, coprocessor or something. It is used for computation, and we can definitely print on it, but printing we would generally like to do on the CPU, because let's say GPU is made for, I mean, it's kind of a computation device, and it's made for computing the large chunk, I mean, computing on the large chunk of data, which have very high amount of, I mean, work that can be done in parallel. So yeah, that's why we offload the computationally expensive tasks to the GPU, and wait for it to finish, and then bring back result to the CPU and then print it. But I mean, if you are saying that why do we, I mean, we can't do it, or I mean, can we do it or not, then yes, we can do it, but we generally don't do it because of this reason. Do CUDA programs
So,
running?
but file system is not available in GPU, no, sir?
Yes, it's not available, but for printing, what will happen is like GPU buffer will be dumped back to the CPU buffer, and then CPU will take that buffer that is dumped by the GPU, and it will print it. Yeah, you are correct that file system is not available, but printing is possible by transfer of the buffer, write buffer. I hope that answers the question. I mean, it won't happen that GPU will send the data to IO or something. It will just send the data, I mean, the printf data to the CPU, and using its, I mean, it will be in the GPU buffer, and it will dump that buffer into the CPU buffer, print buffer, and then CPU will print it. So yeah, you're correct that IO is not there, but yeah, this is the way it is done. I hope that it is clear. Why do, okay, yeah, that is, do CUDA programs run in multiple GPUs? Yes, multiple, I mean, CUDA programs can be written in such a way that it exploits the multiple GPUs, and probably we'll see this in this course towards the end. Yeah, I hope I mean, if anyone have any questions, then
Sir, yeah, one more question, sir.
yeah.
If you look at that syntax of cudamemcopy, does the order of variables in that matter, sir?
Yes, I mean, order definitely matters. First is the destination address, second is the source, third is the size that you want to transfer, and fourth is the direction in which you want to transfer, device to host or host to device. So yes, the order matters. You just can't place destination, I mean, you can't place source first and then the destination, because it might cause multiple issues. I hope it is clear.
Yes.
Okay, so moving on with our slides. So yeah, so this was the typical CUDA program flow, and the functions uh, that are specific to that step in that program flow. Now, important thing to note is this step number 2, which says that we need to transfer data from CPU to GPU and GPU to CPU in step number 4 also, which means that we need to maintain 2 separate copies for each and every variable. I mean, at least the variable that we want to manipulate on GPUs. So we should always, I mean, for example, let's say we want to have want to compute do some operation matrix, then we need to declare CPU mat and GPU mat as two separate matrices on CPU and GPU. I mean, for one which is pointing to the CPU memory location, and another which is pointing to the GPU memory location. Same way for the array. Probably the array example we saw as one of the example in one of the slides, and it's important to distinguish between them by using a proper variable name, like the array, I mean the pointer which is pointing to the memory location in CPU can be named as CPU ARR, and the one which is pointing to the memory location in GPU can be named as GPU ARR, so that we might not, I mean, we might not by chance pass the wrong address to the GPU kernel, and which might lead to some issues like sec fault and all those things that we talked in a couple of slides back. Okay, so that's fine. And now I want you people to try out, or probably try what will be the output of this program, and see what can be the output of this program, and please type your answers in the chat and let me know, like uh, what will be the typical execution flow, and what will be the output. Please try out in probably your notes or somewhere online or somewhere, and please post the answer on the chat. I'll wait for a couple of seconds here, or probably a minute, and then we'll move on. hope that you people are trying. Let me go back to the chat. Okay, no responses up till now. I am assuming that you people are trying. I'll wait for a few more seconds here. After that, we'll see how it works, and we'll see if any one of you have any doubts or anything. Okay. Going back to the chat. Okay, I don't think anyone has typed anything. I'm hoping that you people are trying. Someone has raised. Okay. Do you have any doubt, Ramasamy? You have raised your hand. Hello. Yeah, please go ahead. I mean, you people are raising hand. You can just directly unmute yourself and ask if you want.
Sir, please go first.
Yeah,
Hello
go
world
ahead.
is the answer. Sir, hello world is the answer.
Yes, hello world is the answer, but there is small issue. I mean, I think you might be able to see the issue. There is a small issue with that code. Probably hello world is the answer, but there is something else to it that you should be able to figure
Sir,
out.
one doubt, sir, regarding
Yeah.
the code. If in the
Yes.
code we have like assigned ID, right?
Yeah.
We made like a variable and assigned to it. So like, will it create like 32 different variables, or will there be like critical section or something like that?
No, it will be 32 different variables for each thread. So what will happen is this kernel will be executed independently by 32 threads, and this unsigned ID, which is a variable, which will be separate for each thread, and it will be allocated on the stack of each thread. And as we discussed in previous lecture, stack is separate for each thread, and this ID will be there on the stack, and it will be private for each thread, so it won't create any issues. Yeah, but that's a good observation. Yeah, but that's not the issue. Issue is something else with this code. Okay, if there is hello world is okay, but okay, I'll go back to the slide. I'll tell you what
Sir,
was the
what
issue
about the
actually.
null, sir? Will that get incremented also here?
Yes, that's the issue exactly. So, like, okay, let me explain it. So, see, this is the CPU ARR, right? I mean, this is the string, and its address is being pointed by CPU ARR. Now, there are total 13 characters in it if you observe it very carefully. This first 5 are GDKKN, then sixth character is this /1F, seventh is V and Q 8 9 10 11 12, 12th character is this dash, and the 13th character is the one which is normally appended in the C style string, which is /0, which marks as the end of the string. It is known as end, I mean, delimiter for the string. And that is added by default when we declare a string like this in C. So 13 characters are there right here, and that's okay. This string has size, this array CPU error has 13 characters. Then we have declared a pointer star GPU error. Now what we are doing is we are allocating the memory. That's correct, using GPU error, which will we are allocating the memory of size 12 plus 1. Please note that string length will count up till the /0 character, which is the delimiter. So it will count 12 here by, strlen will count 12 plus 1. So 13 size character array will be declared and its address will be given to the GPU error. So GPU is pointing to some 13 size character array which is allocated on GPU, and it's pointed and its address is pointed by GPU error, which is a CPU pointer. Okay. Now we are doing cudamemcopy, and this is also perfectly done. If you see, we are copying CPU ARR, which is this entire string of size 13, including null character. If you see, of size 13 is being copied from CPU ARR to GPU ARR, including that /0, because strlen plus 1 is 13 and 13th character was that /0. So this is also not a problem. But problem comes here during this dkernel. We are launching the kernel with 32 threads. We are passing this GPU error, that's also fine. But we are giving this strlen CPU error, which is 12 plus 113. And what will happen here is this ARR len is 13. ARR is okay, it's pointing to some GPU string which we allocated here, and we also copied it correctly. But what will happen is this, we are going from 0 to 12. So ID will do, thread 0 to 12 will do this operation. So 12th thread will also so the 12th thread will operate on that /0 character. If you remember that 0th character is this G, and 12th character, which is the last character, 0th character is this, and last character 12th character is that /0. And 12th thread, which will work on 12th character, which is ARR of ID, and ID is 12, will also increment that /0, and that was the end of the string character. And if we increment it, we'll lose that delimiter. And what will happen if we lose that delimiter? It will cause problem in printing, because mostly C style program works in that way. It will print until that /0 is encountered, and if that is not there, it will keep on printing, and it might happen that it might sack fault, or it might give some abnormal behavior. It might also print some garbage value, and all those things can happen. So okay, so why I'm telling all these things? So it's very important.
Yes, sir. It is printing garbage.
Yes, it will happen because as I explained, the reason is that we are incrementing that /0, which we shouldn't do. So the key point that I wanted to highlight from this slide is that we should be very, very careful when we manipulate the strings with the threads. We should always keep track that we are not manipulating the delimiters here, as we are doing in this case. And if that happens, we are lucky here that we are getting garbage. But let's say it might also sack fault, because if we try to access the memory which is beyond the GPU's DRAM or something we try to access, then it might give sack fault also, or process size or something, then it might give sack fault. So this is very important to note, and I would like each and every one of you to make a note of it, so that whenever you write your code, you just don't jump into such issues. And it's very important to keep note of all this. And yeah, so next we'll see the correct code. So correct code is, we need to remove this +1, which is the correct code. And now if you run this code, it will give hello world as the output, because essentially what this code is doing, it is incrementing each and every character of this string. So this string or this character array is first of all declared allocated on GPU, then it's copied from GPU to CPU, then each character is incremented, and if you increment each of the character, you will see that it's an hello world. And then we are copying GPU array to CPU array, which is, we are copying the hello world from GPU memory, which was declared here, to the CPU memory, which is this CPU array, and then we are printing it here. So the result will be very, we all know that it will be the hello world now. And yeah, that's it. And then the main function will return, and yeah, that will be the end of the execution. Yeah, so any questions till now? If anyone have any questions, yeah, so I guess this is correct. It might print some garbage. Yeah. Okay, so if none of you have any question, yeah, please go ahead.
Sir, while incrementing, does the pre-increment or post-increment have any difference there, sir?
Okay, let me go back to the slides. Here, in this case, there won't be any difference, but pre-increment and post-increment will only cause difference if we have, let's say, assignment here. Like, let's say we are assigning the value here to some variable. In that case, it might happen that that variable might get the different value based on pre-increment and post-increment. But for this program, I don't think that it can cause any difference. Yeah, so I hope that answers your question. Gokul, right? Gokul, yeah.
Yeah, sir.
Okay, so okay, with that I'll move on with next slide, probably the last slide for today. And yeah, so last one for you people. We want to write a simple CUDA program to initialize the array of size 32 to all 0 in parallel. So it should not involve any loop. And we want to initialize all the 32 memory locations of the array to 0 using the 32 threads. That's the simple thing that we want. I want every one of you to try and post the answers on the chat. I think it's simple, like it's very similar to the program that we saw previously, I guess. Okay. I hope every one of you are trying.
Sir, the same code that we used for n square, we can just remove the n square and initialize as 0, no, sir?
Perfect, perfect. I mean, we can use that thing. So we can just use that code and it will work. Instead of thread id x.x into thread id x.x, we can just replace it to 0. And that will
also
work.
change n as 32.
Yes, n is 32 because in that case it was 100. Yes. So that will initialize our, I mean, all the elements of our array, which is of size 32 to 0. Now, what will happen if we change that n to 1024? If you do this, I'll probably not tell you people to do right now, but if you do this, you will see that still it will work. But let's say if I go ahead and okay, if I tell you to do this, that you create another kernel and that array that you used, I mean that you initialized to all 0 values, which is now of size 1024, take each element of the array and add I to it for the size 1024. And even this code, I mean this will work. We just need to write a kernel in which we need to write this, right? Wait, I'll go back to chat and tell what we need to write. We need to just do this arr of thread id x dot x plus equals to and I x dot x. Inside a separate kernel, we need to write this statement in order to implement this line. Okay, so that's cool. I mean, we will be able to do it for the array of size 1024 without any issues. But now let's say if I change the size of the array to 8000 and I launch the kernel as we do in the previous case, like this, is to launch kernel like this, right? The kernel 1 comma 8000 and then some parameters here. If we do this, switching back to slides, if we do this, we change this size of the array to 8000 and we launch the kernel as I did in the chat using 8000 threads, then you will see that the code that the kernel that we wrote for implementing this third statement won't work. There will be the issues. And the issue is that the issue is this. So issue is that the second argument, which is this, which we pass to the kernel, it has a limit on it. We can't add more than 1024 threads here. And yeah, there is something called as thread block, which is denoted by the second argument. Sorry, number of threads inside the thread block, which is denoted by the second argument, and that has a limit of 1024. So if you want anything more than 1024 to specify here, you can't specify. But does that mean that we can just launch a kernel with just 1024 thread? No, I mean we can launch kernel with more than 1024 thread. But for that we need to take second parameter in account, and probably we'll see from next lecture onwards how can we make use of that second parameter and can launch the kernel with very large number of threads, not just 1024. Okay, so with this I'll stop today, and I'll wait for the questions from you people.